value the work of your friend.
What do I have to do?
Pay attention.
Is it better?
I mean, like,
Is it better? Is it bigger?
Oh, I think it's
Oh,
better,
Evan's
much
on
better
board.
now.
Evan just unmuted.
Okay.
Okay, okay, so it works now. So this is just us importing everything, right? This is the library that we use. And NumPy is another math library. So let's just do this convention here of using upper cases when we create symbolic variables inside Theano, and lowercase when we have actual values in Python. So this is like what we usually have in MATLAB. Everybody programs in MATLAB, right? Okay, yeah, so MATLAB is okay. So when you print something in MATLAB, you shows the matrix, you got a physical thing, right? If you print this, if you print a NumPy element, you have the physical element. But for Theano, it's just a symbolic, it's just a placeholder in a graph, right? It's like you defining variables, there's nothing in there yet. So this is me like generating a vector and a matrix, and this is the inner product. So you define the whole graph this way, and if you call a function, given the inputs and the outputs that you want to give, f will be a compiled version of everything that you did before. So now, when you do use like physical values, you can pass them as input to f, which is the compiled thing.
What do those arguments mean? W and X?
So w is just a vector, and x is just a matrix.
No, no, no.
You don't have them physically.
String input.
What do you mean?
The string input on the right-hand side.
Oh, just the name? Just the name. It's a symbolic variable, and then this is its name, w. You give it a name because when you have error messages, it will show this name. So if you say like vector w, when it throws an error, that's what it will appear in there. So you know for debugging, what are you doing, right? Okay, so here's like the magic. Because when you call this function to compile your work, it will generate like a optimized C++ code, and then you make the work faster. If you have a GPU available, it will generate like a CUDA function. So those values in here, like a matrix with 4 elements, or this matrix with 10 by 4 values, they are all moved to the GPU, and the operations happens in there, and then it returns the value. Right? So it's like, it's really simple. It abstracts everything for you. You don't have to do any more work. Theano will just compile the function for you. Is it okay? You got that part, Matt? Okay, so for instance, I did that like the inner product of a vector of ones with a matrix of ones. So they have 4 dimensions. So you basically have 10 values, so everybody's equal to 4. Just an inner product of 4, 1 by 1 by 1, some 4. Okay. So, and here is where it's the best part, because you may be like asking yourself, like you were talking about convolutions. I know that neural networks are all about backpropagation, right? If you know neural networks, you know that neural networks are all about backpropagation. But then when I start to talk about convolutions, you may be asking, whoa, how does the backpropagation look like in there? And the answer is like automatic differentiation tools for the case of Theano. There is a way to calculate this convolution, the gradients of these convolutions. You can just do the math and then you see the results. But Theano also abstracts that for you. So what you can do in Theano is, this T is just like the tensor submodule. So from Theano you have the tensor, and then I gave it a shorter name T. And then T has a function that gets a scalar as the first argument, And the second argument is the vector that you want to differentiate with respect to. So we have the inner product, and then you want to differentiate with respect to the vector that we used. And we can compile, this is just another symbolic variable. We can also compile using the GPU this new symbolic function, right? And then if you pass physical values, you have this. So you're basically just calculating the gradient, and then you can create really crazy, really complicated functions and still do back propagation with them without having to care how to calculate the gradients yourself. This is actually, right here is actually the part where several people stop learning Theano, because they already have enough for like using GPUs and making their job easier with calculating gradients. That's what I did in one paper that I had, which was, I just had the idea for an architecture, so I wrote all the equations, and then I optimized the parameters. I was not sure how to calculate the derivatives. I derived them by hand to put on the paper, but in the time when I was like programming, I just used this and I optimized all the parameters of the network, although it was like a crazy architecture, and everything worked fine. Because once you have the gradients, you just do follow the contrary direction of the gradients, like we do for LMS, right? But if you want to see how to basically do that, I have this other example right here. So I created a variable b, which is a scalar, and here's where you can see the different changes. And I gave it a different name. So you have a scalar b, and r is b squared. ASCII r is like b squared, and a is basically the gradient of r with respect to b. So if you have b squared, the gradient of b squared is like 2 times b, right? And then I compiled this just for you to see, and then as a simple input, I chose 2. And then I calculated this, and as you might expect, 2 times 2 is 4. So just to show you how does this work, you can calculate the gradients and compile the function of the gradient and just get the gradient as a result. Right? Did you like this, Evan?
Why is b in brackets there? Those are the arguments?
Yeah, so R, so when you create a scalar, you give it a name, just a string as a name, but when you use a function, you just put the argument for that function. So it's the same thing as b star star 2, b squared.
Why first
In
argument
the
to be
Theano
able to
function,
just
talking about, yes, syntactically,
I didn't understand.
b is in brackets in the Theano dot function. If there were more arguments, it'd be b comma c bracket or
Yeah.
something.
Yeah, you have to put a list.
That's an argument list.
Yeah, because Theano function is expecting a list. If there are no input arguments, you still have to give it an empty list.
Okay. And the output is not a list.
Yeah,
Single outputs only.
it depends. Here the output is not a list, it's just a volume. If you created a list, it will output a list.
Okay.
Later we have lists as outputs.
Can you scroll up a second?
Hmm?
Can you scroll up a second? I mean, I just wondered what, I forgot what T was.
So T is tensor, the tensor submodule. Inside Theano you have tensor, which is just all the functions, all the definition of variables like scalar,
Is anything
scalar,
besides
matrix.
tensor?
Huh?
Tensor's pretty much everything.
Yeah. Yeah. Okay, so so basically you have this. So whatever you're already doing, if you want to use a GPU, you don't want to learn anything. You don't want to learn nothing about deep learning. You already know what you will need. You just want to make it faster. You can do this, right? There's a problem in here, which is you'll be all the time you call a compiled function, it will be moving your data to the GPU, calculating all the operations, and then returning the results, right? Did you get that? Yeah.
Yeah.
Did you like it? Okay, so you can already do that. So just to use a GPU in a fast way, you have all your equations. You may know or may not know about your gradients. You can already do this just to speed up. Just to plain speed up your code, like not doing anything. Or maybe I have a crazy architecture. I'm not sure about the gradients. Also do this. It will do the job for you, and you probably can do much better because it's a computer. It won't mess up, that kind of thing.
So if you just want to do a simple big matrix multiplication, you could do it with a Theano function, and it would be on the GPU instead.
Yeah, and I heard of some people. You know what were they doing? They created a Theano function and called it from MATLAB just to use the automatic gradient. Because, yeah, you know what I mean? So it was like compiler, it was like GPU based, but the guy didn't want to leave MATLAB, so he just uses Theano for this, just to speed up that part. But, as I said, you'll be moving up back and forth from your GPU, and if you have to do that several times, it may be slow. So you may want to do all the optimization without taking your parameters out of the GPU, and you can do that, which is what we show here. So you can create shared variables in Theano. This is how you create a shared variable in Theano. So like Theano shared and the variable, and then I just typecast the variable to be like, if you're using GPU, it's float 32, single precision. If you're using your CPU, it's double precision. So floatx is just theano.config.floatx. It's just like a way to know what are you using, what precision are you using, okay? So you can create a variable, you can create a value, and make it live on the GPU like forever. You don't have to create a function to pass a value to the GPU, okay? So this function is for doing this. So here I created, again, the same example, but this time I put my ones. So now instead of just one scalar, I have like two values. And I make them live on the GPU by calling this function. And now I create my cost function, which is again, just a square, and then I sum those two values. So imagine this function, x squared plus y squared, like a 2D ball, right? And then now, you know, everything is on the GPU. You don't have to pass any input argument. Because everything that you need to calculate, for instance, R, is already on the GPU. The function already knows everything, already has everything it needs to calculate R. Because this is already on the GPU. Did you get that part? Did you get it, Matt? That part?
Mm-hmm.
So you have to be careful with how you name your variables. So when you define R, the name of B has to stay the same, right?
Yeah. You don't change, you don't override your variables. Unless you can like crash your, it's not a problem if the variable is not neither the input or the final output. You can do something like R is B squared, R is the square root of R, you know?
Yeah.
And then you only need the last value. But you still need the input and the output to be explicit. Otherwise, you'll like, the function will not know the entire graph. Is that okay? And here's how you do this part here, this third argument for function is how you do optimization, is how you change the variables that live on the GPU without moving them back to the CPU. You just pass updates, and it's a dictionary where the first value is the variable you want to change, and the second value is like how do you change your variable. So here you have B, and then you have contrary direction of the gradient given a really small learning rate. So that's what I'm doing. So if you use like stochastic gradient descent, that's just that. Okay, so every time you call z, it will calculate r, it will calculate a, and it will update b. This way. Is that okay? Alright, so now, in this example, what I do is I call z, this is me calling z, several times. This is by the way, this is for loops in Python, and it's 10 iterations, and then first I print the cost function. Notice that the output is r, so the output is the cost function that we're using, everybody squared. But I also print the value that is in the GPU. So b is a shared variable, it lives on the GPU, and get value is just to retrieve that value from the GPU. You cannot simply print it, because it will say, this is a Theano variable, that point is a pointer to some spot on the GPU. It's not a value. You gotta use the get function to just retrieve that value from the GPU. Alright. Okay, so, and now you print everything, and then as you know, you start from b equals 1, 1, so 1 squared plus sum is 1, and then after you do the first optimization, you change to 0.8, 0.8, 0.6, and stuff like that, and then you can see that you're minimizing. So this function is basically following the contrary direction of the gradient all the way down to 0. And this is just 10 steps. If you put on 100, it will go to 0. You can play with that code and just change that line. Just run an Python notebook and change this from 10 to 100, and then it will work. Okay, so now that you have enough to sum, now that you know how to sum in Theano, you have enough to do neural networks. It may look like a crazy jump, but it's not. It's just that simple. Here I show you where to download the MNIST dataset. You just unpackage it, and then these lines will be just for loading the dataset. Just an example. First, Pickle is just a load. It's like MATLAB. Pickle format is like MATLAB.mat format. And then you use Pickle to load and save everything. Okay, so inside Pickle you have 3 lists. Each one is a pair of training data and of data and targets. So this is why I get training X and training of I from the train set. And then just to see what this looks like, we get the first row of the training data, and reshape it to 28 by 28 pixels. And then you can see that this is the MNIST data set, so this is a number 5, and the label is like 5, just to classify the number. So, and here's this part of the code. This is one thing. This is just about like details of programming, okay? So what we do with deep learning is we don't have like one example and then do one update right away. We average the gradient across a group of examples. So in this case right here, we were like at every point we update b, right? And then we always follow the gradient. We are here, and then we update b, and then we go to this point, and then update it. Every time we have like at each iteration you do one step. But for deep learning, since you're using stochastic gradient descent, you want to average your gradients across several examples. So usually you get like around like 100 examples. You pass these 100 examples across the neural network, you get 100 outputs, you get 100 errors, and then you get 100 gradients. You average them and then update your parameters. That's the idea. So this, when you play with the code, what you will see this doing is going across the matrix of the training set and just returning. It's like a server, a data server. It goes like across the training set, and then it gets a chunk of like 100 samples at each iteration and gives you this batch of 100 images every time. So this is Python generators. In Python you can do this kind of thing. So for x, y, in batch iterator, I say what are the data that I'm iterating, and what is the size of the training batch. We will call this function batch iterator, which does that. Just cut the data. Okay, and this is what it retrieves at each iteration, like 100 examples of this, of 28 by 28. And the labels, notice that the labels were changed, were converted to one hot. So instead of saying 5, it gives a string of 10 zeros with the number 1 substituted on the 5th position. So this is how they encode the labels. Just for you to see, like an example here, you have like a number 7, and this is its respective label, so 0, 1, 2, 3, 4, 5, 6, 7. So this is how you encode. Okay, and then here, okay, we'll do this, and if you understand that part, you have the idea of neural networks. This is just 2 layers, but you can stack several layers with this code in here. So what I do here is I created this function called rectifier. And the rectifier gets the input dimension and the output dimension. And what is the value that it will operate? So it first creates 2 variables that will live on the GPU. This is the coefficients of your, those are the synapses of your neural network. So it will create this variable to live on the GPU, random variables of 0 mean, and really small variance. This is the variance, this is the size, so it's input dimension and output dimension. And those are the bias, this is the bias. So if you remember, you have like an inner product plus a bias, and then a nonlinearity, right? And then as I showed you before, the nonlinearity is not like sigmoid. It's not hyperbolic tangent. It's either the larger value, either the input or 0. So you have that rectifier function.
SP line. SP line.
SP line. It's the SP line, right? I don't know. SP line?
Yeah, this line.
Oh yeah, yeah.
This
It's either 0 or a line.
Right.
Yeah. They call it like rectifier or ReLU, like rectified linear unit, because you rectify the negative part to 0. And this here is just a function. The outputs of this function is like this. The softmax is supposed to be the last layer of the network. It outputs either 0 or 1 on each one of these outputs, but they also sum to 1. So the idea is it outputs the probability of each label, right? So it's basically just this function softmax. You can Google for softmax to see the equations, but it's basically this. It outputs a probability, a multinomial probability. For this case, we have like 10 labels, right? From 0 to 9, and it will output like, it will sum to 1, and then the largest value is what you believe is the label of that input. Again, does a linear operation, calculates the softmax, which is basically restricts between 0 and 1 and makes sure it sums to 1. And this is the cost function that we use for deep learning. If you have two binary to multinomial random variables, it's either 0, 1 in several dimensions, you just calculate the cost function to be the divergence between them. Understand this as something similar to the error, to the mean squared error. It has a few differences, but it's the same idea, it's the error. How different is the labels that your network output to the actual labels, right? So you have your cost function. Okay, so now that you define how your layers look like, you can build your whole neural network. And first I created X to be like a placeholder, a symbolic variable for what will be our input and what will be our output, the desired values. Okay, and then I just created two hidden layers neural networks. Each hidden layer has 100 neurons, and the last layer has 10 neurons, one per each class. I just created this graph, and then again you just compile the function given your two inputs, the data and the desired labels, and now you have a list of outputs, the cost function and the outputs of the last layer of the network. The output of the whole graph. We are compiling just that. Theano will do optimization of everything that happens in the middle. So if you have like multiplications by 0, or if you define variables that are not used, Theano will not compile it. So it does like some smart optimization like of the code. So it creates like really fast C code. Yeah. And this is one thing that is important. Whether you're doing MATLAB or Python or whatever, always make sure, I was talking to Matt about that, always make sure that while you're creating something that is big, create like partial tests. At least to test if the shapes are what are you expecting. So for instance here, we expect that the output of the last layer is something like, if you have 100 images, you expect 100 images and the labels, right? So we expect the output to be like 110, the dimensions. So you just throw an error just to verify if this happens or not. So always test the middle of the code. Don't wait like till you have everything because your problems may be on the middle, but once you write your tests, I don't write tests. I have computer scientists here. Make sure I know that I don't write tests on the same file. I do things the right way, but you got the idea. Don't judge me. So, again, now we have to just calculate the gradients for everything, right? So we pull in this list all the parameters that we need, and we just scan through them, we just for loop them, and then create a dictionary. We create this dictionary that contains all the gradients of that parameter, of that specific parameter with respect to the cost function. So instead of writing next W0 equals the previous minus, and then the gradient, I just created this for loop. Just be faster, but that's exactly this. It's doing exactly that. It's creating a whole dictionary to work as what we did before, right here. Yeah, here. So I'm just looping through all the variables and creating a dictionary like this. with the parameters of the dates for each coefficient on the network. Is that clear? Did you get what I did in there? Could you do that, Matt? Like, without looking?
I copied and pasted it.
That's how I do code. That's why I use Vim. It's for professional copy and paste programmers. The fastest way to copy and paste code. So I just create this dictionary, and then each place in there just have the variable in its update. Now you can do this. You can create a trainer function with your inputs, the cost function will be the outputs, and every time you call this function, you will do the updates. And that's it. That's all that you need to do deep learning. And now here I go, in this example I went like 100 epochs, and inside each epoch I go through all the batches of the network. So the training data set is like 50,000 images, and I go through 128 at a time doing the updates before I start all over again, and I do this whole process 100 times. And it didn't took that long, but you have like a bunch of, yeah, I don't even know if this one was one of the examples that worked. I don't think so, but you can run it at home and then see the results by yourself. I think I crashed this time. Okay. After you do the optimization, you can also visualize the values that were trained on the network. And this is, for example, one of the features that the network learned on the first layer. Basically, for this data set, the first layer neurons, you learn like strokes. So when you give it as input of 5, each neuron you answer to like pieces of the image. It's like each one is like a stroke detector. Oh, it's this corner. This one actually cares about a stroke of this in this direction right here in the middle. So this is probably a neuron useful for detecting either 7 or 1s.
2, maybe.
Yeah, maybe a 2, yeah, right? Yeah. So not a 0. This is maybe a not 0 detector. Okay, do we have some code? This was not actually a good accuracy, but it's over 90%. You can do much better with more hidden neurons, but you got the idea. Maybe smaller learning rates, training for longer. They usually train for them is like, they repeat this whole operation instead of 100 times, like 1,000. Depends on what you do. It's really fast on the GPU, few minutes. This is just a test, but just to finish this, I'll show you that if you understand the idea of like calculating, defining your graph, compiling it, getting your gradients for free, and then doing the optimization, you can also do more complex neural networks. And then we can finish this. And then, yeah. So basically, what will change here is, instead of the rectifier, Theano also gives you a way to calculate convolution neural networks. Instead of using the dot product, you can use a convolution operation. So inside Theano, or inside Tensor, inside neural networks, inside the convolution, you have this function conv 2D. It's just 2D convolution. And what it expects is an input image and a bunch of filters. And the shape of this is, the first, it expects a tensor of 4 dimensions. So imagine a matrix with 4 dimensions. The first dimension is how many different images. The second dimension is how many channels. So if it is like a color image, is like RGB. So 3 channels. And the other 2 are the sizes of the image. So 28 by 28 in this case. And it expects the same thing for your filters. The first dimension, though, will be the output channels the second dimension has to be equal to the input dimension, and this is the other two are the sizes of the filter. Filter. And yeah, so we do the same thing, just convolution instead of dot product. Again, we do our linear rectifier thing, and that's all. You can copy and paste all the rest of the code. Instead of using rectifiers, you now use conv rectifiers, and then use something similar to what we did before. The same way to calculate the gradients, the same way to update the parameters, everything is the same. And now you're using a much more powerful network. If that doesn't blow your mind, well, it should, because it's something that if you think about it, it saves a lot of time. You don't have to recalculate your gradients, you don't have to define a new function for calculating the gradients. You can rewrite, you can reuse your whole code again. You can create a library to like just get a graph, a bunch of parameters, and optimize everything. That's what we did with that top library that we have in the lab. You just create your graph, and then everything else comes for free. So, from that point, I believe that you can just, so here what I did was, I created 4 layers neural network. The first one has 20 filters of 5 by 5. All those 20 things will convolve with the whole image. And thus the output is like 20 images. It outputs 20 images. And the second layer has 50 filters as input, as output. And they are also 5 by 5 inside again. And here's a little test to just check the sizes of the outputs of the network, of that part of the network. You can compile everything. If you just care about the end results, you can just compile the last output of the network. But for test purposes, you can always compile everything and check what is going on. Also, you want to visualize what is your network learning. For instance, if you learn a classifier, like there is a dog in there, and then you see the middle results of your neural network, you may try to discover where there is a dog detector. And if you go to the famous like Google Brain article, you see like that cat face, which is basically this. They compiled and then they saw what was one of the hidden neurons answering for. What was the preferred function activation in one of those middle neurons, not the last output. The last outputs are just labels. Okay. Yeah. The thing is, the output of a convolution neural network, it gets an input as an image. The output is also an image, so you just flatten it, just like MATLAB reshape. Yeah, you keep the first dimension, which is the number of different images, but you get everything else and stretch as a vector. And now you can use regular neural networks to operate over that. And that's what they call fully connected layers. Fully connected layers means you don't convolve, you stretch all the images and operate at everybody at the same time. It's like fully connected. It's connected at the same time to all the positions on the input image. And Theano just figures out how to propagate gradient through that craziness. Okay, so, and then here, you may have to wait a little bit if you run that code. Another thing that we change here, another thing that we change here is the batch iterator, that instead of just slicing the matrix, now it also reshapes the images to 28 by 28. So now you have 128, just one channel because it's a gray image. There's no color, so just one channel. And then you reshape the images to 28 by 28. And that's what it returns. So here, instead of like 1000 but 784 like before. Now you have like reshaped images. In the network, you operate all over those images. But the things are the same. The labels are the same. If you plot everything, it's the same. You can calculate, so again, just copy and paste it. The same thing. You calculate the gradient the same way. It's all symbolic. Theano figures out how to calculate the gradients for you. And you can train, this is also copy and pasted. Yeah. So that's it, guys. That's, at least you may be able to like, go through this carefully and you should be able to start reading Theano code, and maybe next time we can do some real libraries for deep learning, but make sure you first understand how to read this language, because everything is built on top of it. I was writing DPCN on top of it, like using this, so to understand what I did and to use what everybody else is also doing, make sure you first learn how to read this language. Just to give you like an overview of why you may be thinking, oh, this is yet another language, why is this important? For deep learning, you have three main frameworks. One is called Caffe, it's in C++. It's used by, for example, people at Google, people at Flickr. There's Torch, which is in Lua. If you're not from Rio, which is where it was invented in Brazil, or doing video games, you may have never heard about Lua before. And there's Theano, which is in Python, and it's used by several companies as well. Torch is used by Facebook, by the way. Theano is something used more by startups, but it's in Python. And I believe between these three languages, this is probably the one that is easiest to read and use, because Python is the closest one to MATLAB, I believe. Torch maybe as well. But this is something that everybody is using. So if you go out there and you see an important paper, chances are it was written in one of these three frameworks. And if you know that language, you know that guy's work, and then you can build things on top of it. So take your time, go through these examples, and teach yourself this. If you have any doubt, you can always ask me any question later. You were saying something?
So you just build the architecture as each layer is a symbolic function, and then Theano takes care of the gradients automatically, pretty much for whatever type of network you're making, right?
Yeah. If at first, doing the parameter optimization is kind of complicated, like using Theano itself. You may like, oh, dictionaries, come on, what is this? But you can still just do what, as I said, just compile the functions and use the way you already the way you already do your optimization, the way you already do your LMS algorithms and stuff, just using their gradients and their optimizing functions for the GPU, and you will already get a speed up. Of course, if you do everything without leaving the GPU, it's faster, because there is no moving back and forth. And then what we were asking for Means Lab is like, can we write this whole thing, and instead of compiling to the GPU, can we compile this to a cluster of computer? That's what he will do for us.
Hopefully.
Hopefully. But that's pretty cool. That's pretty cool. Because instead of just doing your operations in one GPU, you do across computers, and maybe across GPUs inside a computer.
If you want to keep it on the GPU, you have to declare every intermediate variable as a shared variable.
Just the parameters of the network. You can do, yeah, just the parameters of the network. The parameters of the networks are the shared variables. They live in there. You just get them at the end of the training. But the batches, like the input images, they change every time. They change every iteration. So you don't have to put your whole data set on the GPU. You just move to the GPU small pieces at a time.
Yeah,
Okay.
No, I have a question and for maybe looks not very, maybe I didn't understand very well, but yeah, I'm still thinking, the comparison between the neural network and deep learning, and except for the convolution part, your code, you said that, for example, at the beginning in the introduction, that for the input of each layer, right? You have more layers, and the input of each layer is going to be considered as like independent of the other one, so like a new problem. So the Theano, it takes care of that part. I mean, how the code is different with the neural network?
There's no difference. That's actually what makes people feel like, what is going on? It's basically more layers, more data, larger architectures. Because before, I mean, we're research scientists and we have like 4 or 5 years to finish a PhD. We are not willing to wait like a whole day just to know, oh, maybe my learning rate should be a little bit smaller. You have to tweak with those methods, right? And it takes a lot of time. And then you create several things with several different parameters and then you run them in parallel and that kind of thing. Now it's just faster. So people tweak more and they get results right away in time to have an intuition of what each parameter means. Just because it's faster and they have more data, the network doesn't overfit as fast anymore. So the way you code, basically this, you can say like the first neural network you coded was like a regular neural network, just a different cost function. Yeah, exactly. The way to make that network, that exact network, like break the benchmark and like work as the best number recognizer is just change a few. You change a few parameters in here. For instance, the gradient. This is like plain stochastic gradient descent. In the first slide, I show several optimization algorithms, and it's basically changing this line. So you change a line, you change the optimization algorithm, and it converges faster. It doesn't get as stuck in slow gradient regions. But the code is the same, exactly the same. What actually changes are those small tricks. But yeah, sometimes it's just hard to understand everything on the papers, and when you go to the guy's code and it's written in Theano, then you go like, oh, okay, now I understand what they're doing. I don't know if you have that feeling, but for me at least, sometimes it's better to read their code than their equations. It means they are not doing the right equations. The mathematicians stare at me and say like, those guys don't know how to write equations then. But yeah, that's what happens.
I agree.
Okay.
So this is available at Éder Santana GitHub, right?
Yeah.
Just go to
GitHub.com/Éder Santana, and then you go to the deep life coding demo.
So if you guys, we don't have everybody's email address, so if you want to see the code demo, what is that?
GitHub.
Oops, GitHubs.
GitHub.com. Éder Santana. The slash again. Deep life coding.
They'll find it there, right?
Oh, okay, yeah. Yeah, deep life coding. That one. You can go to there, and then you can play with that code. Just make sure you have Python installed. There's if you look for Anaconda, just like Nick Minaj Anaconda, Python, you find a distribution with NumPy, SciPy, everything already installed. And then you can just go straight away to IPython notebooks and run that code. If you have any problems, or like, hey, how do I start an IPython notebook and stuff like that, you can always ask me. I'll be around, and you guys on the same floor, so.
Is Theano a library? Do you need to download it to use?
Anaconda already got Theano,
Okay.
so you don't have to install. It's also available in GitHub. You can install it. You can use Python package manager to install it.
Doesn't come with Python though.
It doesn't come with bare Python.
But it probably comes with Anaconda distribution.
Yeah, so if you install the Anaconda distribution. So yeah, hopefully at least we can get some of you to start playing with that. I would consider this successful.
Alright, well, thank you, Éder.
Alright. is paying us free pizza. Pizza for everybody, right?
Forgot about that.
What are you paying? Oh, wait. Were we working for free, man? Come
We're
on.
going to order pizza, we forgot.
Hey, do you know the Yuki's